This is a demonstration of learning topology of mesh microgrids using voltage magnitudes. The project was funded by US Department of Energy through the CyDERMS Project. The work was performed at the University of Minnesota. Here is a brief overview of the topology reconstruction methodology. Assume a power system operating in real time and voltage magnitudes at different buses of the network are being measured and sent to an algorithm. The algorithm then uses the voltage magnitudes to reconstruct the connectivity structure among the different buses of the network. The algorithm that is being used in this particular presentation is called the sign rule based topology reconstruction algorithm. The algorithm uses the inverse of the covariance matrix of the voltages to identify the connectivity structure among the buses of the network. More precisely, the algorithm examines each of the entries of the inverse of the covariance matrix and checks its sign to identify whether a link is present between two nodes of the network or not. Next, a demonstration of the voltage magnitude based topology reconstruction is shown using OpenRT based real-time simulations of a modified IEEE 33 bus network. The hardware setup used for this demo is shown on the slide here. The setup consists of an OP5700 real-time simulator, which is capable of emulating power systems in real time, a visualization screen for graphical user interface capabilities, and a server station, which is used to deploy a custom-built software stack. More details on the custom-built software stack is provided in the later part of the demo. In this demonstration, a modified IEEE 33 bus power network is used to showcase the performance of the reconstruction algorithm. An OP5700 real-time box simulator is used to simulate the test system in real time. We are using the eMagasim platform of RTLab for the simulation. The schematic of the RTLab model is shown in this window here. As the name suggests, the system contains 33 buses connected through predominantly resistive lines. The lines are depicted using the yellow colored boxes in the simulation model. The buses are depicted as the blue colored boxes, and the loads are depicted as the green colored boxes. Each of the loads are modeled as variable PQ loads that are playbacked into the RTLab model during the real-time simulation. It can be observed that the system contains loops in the network, making it a meshed network. During runtime, there are 33 emulated digital RMS meters which are measuring the voltage magnitudes of the buses. These measurements are then transmitted in real time to the emulated sensors via UDP communication protocol. This concludes our description of the real-time simulation model. To perform the data collection, visualization, and running algorithms, we use a custom-built cyber-physical infrastructure built at the University of Minnesota. A visual depiction of the cyber-physical infrastructure is shown in the picture here. The backend engine, which is the main server, facilitates connection between the visualization, algorithms, physical layer, and the storage controllers. Now, let us move to the custom-built backend, GUI, and algorithm and see how they are integrated together. We have the front-end GUI open on the left of the screen here, and we have four consoles open on the right to perform four different tasks. First, we initialize the backend in the first console here. As it can be observed, the backend functionalities are now live in the background. We can press stream network here, and that will push a network to the front-end GUI here. So far, we have not started streaming data and do not have the topology connectivity information yet. As a result, we have a network with no edges on the front-end GUI here. Now let us enable the sensors interface and attach the sensors to it. As the sensors get attached, you can see the nodes here turn green. Next, we start streaming data from the OpenRT model. Next, let us start collecting data that is being streamed. As it can be observed, the data samples are being recorded here. The simulation is set up in such a way that the data samples are recorded at an interval of 100 milliseconds. Once adequate number of samples have been collected, the sign rule algorithm will be executed automatically, which will produce a network topology, which will be forwarded to the backend system here. And the backend system will relay it further to the front-end GUI, which will show us the actual reconstructed topology. For this demo, the required sample size was set to be 3000 samples. So once 3000 samples have been collected, the reconstruction algorithm will be executed. After 3000 steps, the console shows that the Python algorithm is being executed and the network reconstructed is shown on the GUI over here. This concludes the live demo. It can be inferred that the topology reconstruction approach can be helpful in many different real-world applications. Such scenarios include situational awareness applications in power systems, change detection in power networks, and line spoofing detection in cybersecurity applications.